So we are still missing one more Hamza. There's one missing, and I suppose it's Deepali. Yeah. So we will. We're still expecting another Hamza to appear. But yeah, so I'm really happy and proud to introduce the Monash EBS contest. We have 3 participants today. We have Cynthia Huang from Monash. We have Deepali, who's gonna, I hope, join us soon. So Deepali already answered by email, so I'm sure that she knows about today, but I hope there won't be any confusion regarding the change of time and the different time zones. Deepali is from Department of Mathematics, Institute of Chemical Technology, Mumbai, India. And we have Shirin, who has already joined under the name Hamza, also from Washington State University. So I'm really excited to hear what you guys have to present. Cynthia, please, you can share your screen and tell us about your research.
Great. Can everyone hear me? Yeah.
Yes.
Good. Okay. So, and can everyone see my screen?
Yes.
Okay, great. Well, thank you, everyone. So my talk today is on my research on ex post harmonization using graph representations of cross taxonomy transformations. It's quite a long name, and I'll kind of explain what each of these things means. But to start with, ex post harmonization refers to procedures applied to already collected data to improve comparability and kind of use the data in a combined way, even if it wasn't collected with that purpose. So typical examples include kind of labor statistics from different years, where you get kind of the introduction or removal of different occupation codes across time. Can also be kind of macro or trade data involving product or industry classifications, or even changing country boundaries. And that's also in the case with census and election data. You kind of have changing statistical areas. And so to use data in a panel, you need to combine data that's kind of being collected under different taxonomies. So the process of doing ex post harmonization can kind of be broken up into a number of subtasks. You have the kind of collection and cleaning of each observation. So you might have some set of data, let's say for Australia, of like labor statistics and accounts by occupation. You also then need to design what the transformation is going to be and select kind of a target classification, say some international standard for occupation codes. My current research focuses on the transformation stage between a source taxonomy and a target taxonomy. So if you can kind of imagine that the observations are collected using some source taxonomy, like a given list of occupations, and we're kind of transforming it into some kind of counterfactual observations where it was collected under the target classification that we're interested in. And so kind of just definitionally, I use the word taxonomy kind of loosely. It's a bit of an abuse of terminology, but I haven't yet found any better terms for it. But we have source and target defining the kind of set of categories, let's say occupation codes, which the data is collected or transformed into. Category indexed values are the kind of numeric index pair where you have, let's say, teacher and some count for the teacher would be an example of a category indexed value. And an observation is basically a set of index values for a given observational unit. So that could be Australia for 2020, and then the observation contains all of those values. So, the count for teacher or lawyer, and so on. So the motivation and kind of background for looking at this particular subtask of data preparation kind of comes from 2 angles. One, a kind of practical data wrangling angle, which is that having a standardized workflow kind of improves code readability and reduces errors. So there's kind of precedent for this in kind of domain-specific languages for data preparation, including the kind of tidy data framework that's implemented in R, as well as the Wrangler language that kind of powers some commercial data preparation tools. The second motivation is from a statistical point of view, the properties of kind of complex pre-processing decisions are not really well understood relative to simpler transformations like missing data imputation. And formal structures can actually enable us to analyze these properties. So what are the existing approaches to doing this type of transformation? In general, you'll have some source data that maybe you collect from an official statistics organization or some other kind of survey source. And people will then write some sort of script, often quite varied and idiosyncratic script to transform that. And as part of that, they might also try to validate the data in relatively kind of ad hoc ways. The approach that I propose separates the kind of definition of the transformation logic from the implementation on the data. It provides kind of a standard framework for validating the transformation logic using graph properties. And so what exactly is a cross-map, right? So cross-map is the data structure that I define to encode the transformation logic of taking data from one taxonomy to another. And as a kind of first representation, you can think about it as a bipartite graph where the source and target sets of categories form the two disjoint layers of nodes. And the weighted edges actually specify how numeric data is transformed when you go from one taxonomy to another. There's a lot of ways to kind of look at this transformation, but if you kind of take a step back, you might also see that this is actually defining a conditional probability distribution. So let's say that we're starting off in category F, down the very bottom. For any observation that's within that category, right, there's some probability that, let's say you started off as data scientist in this first survey or taxonomy, and then in the counterfactual world, you have some percentage chance of being classified as, let's say, IT professional or some kind of target category, right? This kind of alternative representation becomes useful in a second when we think about validating the transformation logic. Other useful representations of this transformation are as a transition matrix, right? So a graph can also be represented as a matrix, and it actually highlights that cross-taxonomy transformations can be thought of as a special case of Markov chains. And then obviously an edge list representation allows for the transformation to be implemented as a series of database joins. Right? And so when we're building like a data wrangling tool, we can use the database joins to actually implement it rather than dealing with graphs or matrices. So what are the implications of being able to kind of unify or represent this transformation as a cross map? So if we think about what forms a valid transformation, basically when you have data in a source classification, you should preserve the total when you transform it, right? So if you started off with, 1,000 survey respondents that are then kind of grouped by occupation, after you change the kind of naming of the occupations or the occupation list, you should still only have 1,000 people, right? So in that transformation, you shouldn't lose any data, you shouldn't create any data, right? And so if that's the case, we can actually check that a cross map defines kind of valid logic if every source node and its links define a valid probability distribution. Or in other words, the sum of the edges coming out of each source category sum to 1. The other kind of implication is that there's actually no way to meaningfully distribute missing values across multiple categories. And so you should deal with your missing values before you actually try to do the transformation. And this is based on kind of the existing algorithms that I looked at. People do try to pass missing values through the transformation because it's not immediately obvious that that doesn't make sense. Okay, so then implications for kind of code readability. Essentially, you can go to using just, in my implementation, just 3 lines of R code to transform data, given that you have a validated transformation object, so a validated cross map, compared to kind of hundreds of lines of code for like imperative algorithms. So this is an example that takes some trade data from a HS classification to the next classification. These are all kind of product classification standards. And you can see here that there's kind of 800 plus lines used to define the transformation, which also makes it, one, very difficult to read, but also very difficult to check the accuracy of the transformation. Lastly, I want to talk briefly about the implications for kind of the statistical properties of this type of preprocessing, and highlight that even if you have a kind of theoretically valid transformation logic, that doesn't actually guarantee that the transformed data is kind of sufficient quality to kind of support downstream inference or estimation, right? In practice, the quality of your transformed data depends on the quality, obviously, of the source data, right? So if you collected garbage data, you can't transform garbage into, informative data. It also depends on the quality of the cross-map or the mapping that you decide, and that often comes down to kind of domain knowledge, right? To say between two classifications, which occupations or which products are most similar, right? So which ones can we actually say are similar? But it also depends on the degree of imputation that actually occurs when you're transforming the data, right? And so we can think about these transformations as a kind of complex imputation procedure, and kind of relative to something like missing value imputation, where you can just do a count of the missing values and get a kind of a percentage to say, 10% of the data was missing and we imputed therefore 10% of the data. It's actually not immediately clear how to define a metric for measuring the degree of imputation for cross-taxonomy transformations. But this framework suggests that the metric needs to incorporate properties of the graph, so graph properties or kind of properties of the mapping, as well as some notion of distance between the source and transformed data. Finally, we can also use this definition to see that we have a class of graphs that we can essentially generate alternative transformations for a given set of source observations. So, for example, if you have some labor statistics from the Australian Bureau of Statistics, they actually publish concordances between years for transforming data. You could think about forming a different transformation for that data using these properties. And then you could look at like the robustness of downstream analysis to kind of different mapping decisions. So some other related work is that I am doing with this approach is an R package implementation of object classes and functions, database functions for this approach. And I'm also working on kind of using this structure to define certain data provenance or documentation artifacts. So using graph visualization to actually visualize what's happening in those transformations, identifying kind of influential links. So an example would be if you have in your transformation one-to-one renaming, that's kind of whatever relative to one-to-many splits. And the last thing we can do is actually extract transformation logic from existing algorithms. There's certain conditions that have to be met for this to be possible, but for example, from that 800-line script, you could extract parts of the transformation as a cross map and then get visibility on that. Yeah, so that's the end of my talk, and open for questions.
Thank you very much, Cynthia. Any questions? Yes, David.
Hi there, Cynthia. Could you go back to your conditional probability distributions and maybe take another minute to try and explain that again? I think it was a little bit too fast for me.
Yeah, okay, sure. So basically, if you think about having aggregated like occupation statistics, right? So I have, 100 teachers, 50 lawyers, and then I have some other naming for these categories, right? Or some kind of sub hierarchy, right? So instead of teachers, you get like assistant teachers and whatever, right? And so conditional on a individual being in this group of teachers, right? If we have some like 3, for example, so I was looking at this bottom one, right? So we replace F with teacher, right? And then you have, assistant teacher and substitute teacher or whatever as your 3 categories, right? Conditional on starting off in teacher, once we move to the transform data, right? So like in this kind of alternate state of the transform data with, probability of a 30%, 30%, and 40%, you kind of end up in one of these other target nodes, right? And then on aggregate, that actually defines then what the proportional transformation of the data, right? So of the total count, let's say you start with 100, you end up therefore with like 30, 30, and 40. The reason I think that's useful is that when you're checking the transformation logic, you just have to check that the graph forms, each of these kind of disjoint subgraphs forms a valid probability distribution.
But it doesn't matter the weighting of the probability distributions in the final analysis?
What do you mean by it doesn't matter?
So the corresponding weights of the conditional probabilities, how F is mapped to all the subclasses, those are always going to define a subgraph that makes sense, right?
Yeah.
But depending on the allocation of those weights, I could have completely different outcomes on the inferences.
Yes, exactly. Yeah, you could. And so that's kind of what I'm trying to highlight here, which is if these decisions are hidden within this kind of imperative code, you actually can't see what decisions are being made, right? But by extracting it into this like formal structure that is like well-defined, we can start to analyze it and actually maybe reason about it. Yeah.
Okay, cool. Thanks.
Catherine, question?
Hi. Yeah, thanks so much, Cynthia. So my question is really about who you think the end users are most likely to be. And if you think of, is it one type of user, or are there, main classes of users? I mean, who do you imagine would be most able to benefit from this type of package or concept?
Yeah, so I think because it's actually an information structure and there's different ways to use the structure, it depends what you're looking at. I think the end user is somebody interested in the kind of provenance or the kind of sensitivity of analysis to these kind of decisions. And I think that kind of in an ideal world, it would be great if kind of official statistics bodies were actually publishing some of their data documentation using the structure, because they do often publish guidance on how to go about ex post harmonization, right? So they might have, multiple releases of some data. And I like the example of occupation statistics because I think it's easy to understand why that changes over time. But they publish concordances. But concordances are actually just the unweighted version of this graph, and they leave the weighting often up to, other people to form some sort of algorithm on how they actually approach that.
Great, thank you.
Thank you very much, Cynthia, for the presentation. Can I ask you to stop sharing your screen?
Yes.
Thank you very much. It was very insightful. And so now it's time to move to Deepali.
Yes, I can.
Are you ready, Deepali?
Yes, I am ready.
Great.
Okay, so I'm audible to all, right?
Yeah, sorry, quickly, I actually forgot something important to mention. David and Catherine and Julie, maybe you can raise your hands. Yes, so that's our panel of judges. Also.
Okay, hello judges.
Hello.
Whenever you're ready, Deepali.
Yes. Hello. Hello.
Yes, can
I
hear.
can hear you.
Yeah, so you can see my screen, right?
Yes.
Okay. So hello everyone. My name is Deepali Mistry, and today I am going to explain our findings, and this is our article which we soon be submitted in one journal. So the title of my presentation is Identifying the Key Drivers of Extinction for Chitala Population. Data-driven insight for the Chitala and integrated predation model using Bayesian framework. Oh, sorry. There is a technical problem, I think. Sorry. Hello.
Yes, we can hear you.
But I'm not able to move from one slide to another slide.
Maybe try to stop sharing and then set it up again and share again.
Or Dipali, you can also send a copy of it to Shayanti, who as the host can share for you, but
Okay.
so stop share and then start share again.
Okay. So
we can see you on screen. Just stop the presentation. Go to your presentation.
So Dipali, in the, keeping time into account, why don't you just email it to Shayanti? Shayanti, as host, you can share the screen. And then maybe Shirin can get started right now, and then you can go to the next one. Then you will do at the end, okay? In the meantime, just email it to Shayanti.
Yeah, let's do that. Shirin, you're ready?
Yeah,
All right, great. You have 20 minutes.
1 second. Right, let me.
Dipali, just go after Shirin, okay? Yeah.
Do you see my screen fine?
Yes.
All right, perfect. Hello, everyone. My name is Shirin Shahsavand. I'm a PhD student in operations management at Washington State University. I got my master's in statistics from the Department of Statistics and Mathematics from Washington State University. And I'm very happy to be here and to discuss with you my ongoing research project, which is looking into the impact of female inspector presence on FDA inspection outcomes. So even when we are constrained by bureaucratic rules and roles, there is a difference in the way women and men perform their duties. And these differences are more, basically, they manifest more in highly regulated settings, such as the US Food and Drug Administration, because women tend to be a little bit more rule conscious and they're more persistent in pursuing their assigned tasks. The more rule-conscious nature of women, along with their perceptual and integrative processing, may enhance the way they actually cite infractions. And in addition, they can also incorporate more evidential clues in than men, and they can also have they're better at interpreting the emotional content of others, which is really important when you think of a manufacturing plant setting. And that's why I think it's reasonable to expect that the presence of women on inspection teams for the FDA actually may impact the outcome of inspections. So let me tell you a little bit about FDA operations. FDA actually oversees about 13,000 medical device facilities in the US, and they do routine inspections about once every 2 to 3 years. So FDA district offices assign these inspectors to conduct these investigations, and the investigators actually go and collect data, evidence, discussions, and interact with the workers at the plants to make a decision about whether or not the firm complies with all the FDA regulations. So they can give a no action indicated result as an outcome to the firm, which means that they haven't found anything objectionable, or they can give a voluntary action indicated result, which means that they have found something, but it's just they're not ready to make an official recommendation. And they can give official action indicated, which is the most severe outcome that could come out of an inspection. And that means that the firm is actually in trouble and they have to make significant changes to their processes. So in terms of severity, we go from an NAI outcome to an OAI outcome, OAI being the most severe, VAI moderately severe, and NAI not severe at all. So when we look at the literature, and just let me actually pause a little bit and talk a little bit differently. So I come from an operations management background, so we tend to be a little bit more application focused and data focused, and we use a lot of data, but our research is a little bit more about applications of data to operations and decision making. And this is where this whole project comes from. So I'm looking at the role of gender in decision making, and there are a lot of publications, particularly quite recently, that look at the role of female directors and females in management positions. For example, Wolwack and her co-authors look at how the presence of female on board of directors actually impact FDA recall decisions. Post has a couple of publications that look at management decisions made by women. And on the other side of things, inspections on audits and regulatory audits, we have a lot of papers, excuse me, that look at how those are done and what are the impacts. In a very related work, Short and her authors look at actually the factors that impact decisions in inspections and audits. And they actually find a very similar result to ours, but that's a very small part of their paper, and they basically touch on it whereas we go a little bit deeper. Ball and his co-authors also look at FDA inspections and the impact that the outcome has in terms of quality after the inspection. So we tend to kind of fill this gap right in the middle, looking at the role of gender in decision-making and with respect to inspections and audits. This whole thing is started with this question that how does the presence of female inspectors impact the outcome of FDA inspections? And we know that there is so much evidence that shows women are more rule-following, they're more thorough. So because of that, we hypothesize that the presence of female inspectors is positively associated with more severe inspection outcomes. For the same reasons, we also expect that a higher proportion of female inspectors is positively associated with more severe inspection outcomes. And because they're more thorough, we tend to see a longer period of time for each inspection when females are present. And we hypothesize that that's what mediates this more severe outcome. And then last but not least, the question of, so what? What does this mean? So we hypothesize that the presence of female inspectors is actually associated with a smaller number of adverse events in a period after the inspection. In terms of the data, this was actually a very fun part of this project. We combined multiple data sources. Our original data source was FDA inspection data for medical device manufacturing operations from January of 2000 to December 2019. We decided to exclude COVID because everything just was different. Inspections were conducted remotely and all those things, but we included everything for that 20-year span. It had all the inspection details, including the dates and the outcomes and the firm information. It also included the names of the inspectors that basically conducted the inspection. And what we did was we used a genderized software to predict the gender of those inspectors. And this is a well-established method in operations and in marketing. Actually, they use it quite often, that they use this to basically predict what gender the inspector has or what gender, just based on the name. And then once we did that, we also gathered some publicly available FDA data for device registrations, district offices, and reported adverse events. And the data that I'm talking about, at some point, I was handling about 48 million records. So it's actually pretty ginormous for, even though it's not, it doesn't feel like it, but it's actually, we used a lot of data to come up with the results that I'm presenting today. So after all the cleanup, everything that we did, we ended up having about 10,610 inspections, unique inspections. We had about 4.5% OAI outcomes, which is the most severe outcome, for about 2,900 unique device manufacturing plants. And as you can see, most of the inspections are done with just one inspector. That's why we see such a number close to one for the average inspector per inspection. But there were a number of, I think about 14% of our data had multiple inspectors for the inspection. And then the average inspection length turned out to be about 6.5 days. So the way we went about predicting the outcome, the most severe outcome, which is the OAI, was using logistic regression. And to do that, we controlled for a lot of factors, which I'll talk about momentarily. And for the our third hypothesis, we used linear regression. So in terms of variable, we basically, our independent variables were female presence, female proportion. Again, for the mediation effect, we looked at female presence and inspection length. And then for our adverse events, we look at the OAIs given by females. To control for different factors, we looked at prior inspections, prior OAIs, number of devices, inspector experience, which has shown to have had some effect in prior publications. We didn't find any significant effect in this work, but we also included fixed effects for facility, district office, and year, as they could have impacted the way inspections, the result of the inspection. So through all of this analysis, we found significant support for our first hypothesis. And we found that the presence of female inspector is associated with a high probability of an OAI outcome. We also found that a higher proportion of female inspector is positively associated with more severe inspection outcome. So as the proportion of females go up on the inspection team, the likelihood of getting a severe outcome increases. And we also found that the mediation effect is there, and it definitely, the inspection length mediates the relationship between severe outcomes and female presence. What we interestingly found was that female presence is actually associated with a larger number of adverse events following an inspection. This, we did not expect this, and it is a very, very robust result. So I've tried testing it multiple times, trying to kind of do supersets, subsets, every variation that could have potentially made a difference. it looks like it's there, and it looks like presence of female is actually associated with more adverse events. And we are theorizing, we are trying to understand what's happening in the background, trying to figure out why that is. Maybe it's because people don't listen to females as well as they do to males. So we don't know that mechanism yet, but we are working on that. But in terms of robustness, we did have some concerns about endogeneity with our independent variable. And we did instrument for the variable. We actually found a very strong instrument using the district office data. And we found that our results were statistically identical, which was actually very reassuring in terms of endogeneity. We also ran our model on various subsets and supersets. As I mentioned, we tried a lot of variations. We tried relaxing a lot of our assumptions, and our core results remained the same. So in summary, as I said, the presence of female inspector, we found that it's associated with a higher likelihood of severe inspection outcomes. The likelihood of a severe outcome increases with the higher proportion of female inspectors, and also this relationship is mediated by inspection length. Again, I'm not talking a lot about our adverse events, even though that's actually very interesting, because that's something that we have recently worked on, and we are trying to figure out the mechanism, but hopefully I'll get to share it with you at a later time. Thank you so much. I really appreciate you guys being here, and please let me know if you have any questions.
Thank you, Shireen. Any questions from the audience? Yes, Catherine?
I think my hand was still up, but I do have a question. I thought it was down. But I do have a question, actually. So thank you, first of all, for your presentation. It was interesting to see the kinds of questions you're exploring in this environment, which I think is kind of curious that, I mean, you think there'll be an effect, but it's interesting. I didn't know about that literature. My question really is about the genderizing prediction of, the prediction of gender based on the name. Because I don't know if there's literature on this or not, but just anecdotally, it seems to me that there's an increasing tendency to use, in particular, male names for females. Maybe it goes both ways, but I definitely think there's evidence of that. So there would, in any case, there would be some error in the prediction. And I wonder if you had taken, or if you had any information about the rates of error that are likely, and if you had maybe some way of incorporating that uncertainty into your analysis.
Yes, so the way the prediction works is actually it gives you a probability of a name actually having a certain gender. So what we did initially was to make sure that my data is robust and real. I only used everything that had a 95% more probability of being a certain gender. And then to basically check the robustness, I also checked everything that was above 90%. So I actually Googled every single person's name that was above 90% and tried to match their gender with their, it's not a very objective way of doing things, but it's very accepted. And to be honest with you, I did run the analysis on a very smaller subset with the names that were, it's very unlikely a woman is named David. So with those names, I tried to basically look at the names that are highly unlikely to be a different gender, and the results are still robust. So there is a degree of uncertainty. We do tend to use multiple people. So there was I had a research assistant who was helping me going through these records because I didn't want to be the only person making a decision about this. So we both did this double checking of everything that had a lower probability and came out with the results.
Okay, thank you.
Thank you, David.
Hi, thanks, Sharon, for your presentation. I had a question regarding the models themselves. You showed 3 of them. and I was wondering if you might be able to go back to that slide real fast. Yeah, right
This one?
there.
Yes.
Yeah, so H1, H2, H3 refer to different dependent variables, correct?
Yes.
And you're fitting each of these individually, correct?
So can you repeat that that last part?
So you're fitting Y as OAI, right? But there's also two other classifications, correct?
Yes.
And
So
so-
we did run everything. This is basically, so the OAI tends to be the most significant. Actually, it is the only highly significant result. So the difference is only apparent in a severe outcome. The other two, so our data is about 10,600 records, about 4% is OAIs. The rest of it is 50-50. So there's like 46% NAIs, 46% VAI. So it's about the same proportion. And it was interesting that we did also multinomial logistic regression, and it is still held up. So OAI with respect to NAI and with respect to VAI, it's always positive coefficient for female. Whereas,
Sorry, go ahead. I guess what I'm trying to get at though is that kind of presumes though that OAI and the other two are uncorrelated. When you're fitting multinomials or when you're fitting regression logistics together, and you're assuming they're not correlated between those. I would assume they would be.
They are. So we control for the prior. We do control for the prior inspection outcomes. We also originally we did control for both prior NAI and prior VAI. They seem to be very, very insignificant. That's why we didn't end up including it. But we do control for every possible, everything that could potentially be correlated with an OAI outcome.
Okay, cool. Thanks.
To the best of our knowledge. There's probably something out there that we're not controlling for, but to the best of our knowledge, we are.
There always is.
All right, thank you very much, Shireen. Thanks again, David and Catherine, for the questions. Maybe we can try again with Deepali. Hopefully this time it will work.
Yeah, I just had wanted to clarify one thing. Since we have like about 15 minutes left, so how much time for presentation are we looking for Deepali?
Well, hopefully if Deepali, if you manage to finish a little bit before 15 minutes, then we can have a few minutes for questions. Otherwise, just go with your presentation.
Let me know if you can start, otherwise I can share.
Yeah, hold on.
Stop sharing.
Slide.
Share.
Now screen. This. Now, Shantini ma'am, can you please share this
I
screen?
will share. I'll share.
Okay.
Right.
So, good morning, everyone. So my name is Deepali Mistry, and I am explaining about our works, which is the identifying key drivers of extinction for Chitala population, data-driven insight from an intragrid predation model using a Bayesian framework. Next slide. So this is the agenda of our talk. Next slide. So starting with the existing research, the fish species Notocorus chitala is a freshwater fish and which is widely distributed in African and Asian countries. And it is categorized as a endangered species in the Conservation Assessment and Management Plan 1998. Next. So according to the recent survey conducted by Conservation Assessment and Management Plan in the stretches of river Bhagirathi Farakka, which is in West Bengal, India, reveals that around 70% Chitala population has been declined in the past decade. Parup et al. In 2022 analyzed the potential for the extinction of Chitala by considering the abiotic factor in their habitat. Their result shows that the abiotic factors are not the reason for the decline of the Chitala. So we here have decided to analyze whether biotic factor have an impact on declination through modeling the predator-prey food chain interaction of Chitala using data from their natural habitat. Next. So this is our hypothesis. Is the unavailability of prey is the main reason for the decline, or there are the other reasons? Next. So for analysis, we have considered the data from the three sites. One is Diamond Harbor, Malancha, and Raidigi, which are along the Hooghly River and Vidyardhari River from India. These sites are considered as a three different habitats for the analysis, and data collection have been carried out for the three species. One is Chitala, Mugil, and Shrimp. And the data is of the monthly catch in kilograms for the period January 2013 to December 2016. Next. So this is the data plot for the analysis for the three locations. Next. So these considered three species are interact with each other in the intragrid predation manner. What exactly the intragrid predation means? When in the food chain, the competition and predation happen simultaneously, then we call it as an intragrid predation. In our case, the adult Chitala feeds on the Mugil, while the sub-adult Chitala, while the sub-adult stage, Chitala feeds on shrimp and Mugil eats shrimp. So this interaction is the intragrid predation. So next, we have considered two models given by Kang and Wedkin. And in that model, PT, GT, and MT represent the abundance of shrimp, Mugil, and Chitala. Next. So these are the two models which are the describe the IGP interaction. In first model, the top predator that denoted by M, which is our Chitala, is the specialist predator. That means it depends on shrimp and Mugil for the survival. Whereas in second model, the predator is generalized predator where it can survive without the presence of G and P. The parameter description and mathematical analysis of both the model are given in this Kang and Wedkin article. Next. Next, we convert this deterministic model in the stochastic model by adding the environmental stochasticity alone. So here, because of and DW1, DW2, and DW3 follows the normal distribution. Next slide. Because of this distribution, the resulting distribution is normal, and all the analyses are carried out in terms of relative growth rate. So this is the likelihood for corresponding to M1. Previous slide, please. Where M1 having the θ1 parameter of dimension 13, and similar calculations are carried out for the M2. Next slide. Where M2 has the 14 parameter. So first we have to select amongst the model to decide whether the nature of top predator, whether it is specialist or generalist. So for doing the model selection, we have to first estimate the parameters of both the models. Next slide. So to carry out parameter estimation and model selection, we use the Bayesian statistical method. Next slide. So idea of Bayes statistics is that they considered theta as an unknown but not a fixed quantity, and according to the prior knowledge, they update their prior knowledge through likelihood and get a resulting distribution called as a posterior distribution. All the inference and prediction are based on this posterior distribution. Next. So next slide. So the model parameters are estimated using this posterior distribution, and in R, using the R2JAX package, we use the JAX program to get a posterior distribution of each model parameter, And using this setup, we obtain the posterior distribution of model parameter. Next slide. So for the model selection, next slide. We use the posterior model probability as base factor, as both can be calculated using one another. The base factor for comparing model MI and MJ is calculated using equation 1, whereas the posterior model can be calculated using base factor using equation 2. But in equation 1 and 2, if the parameters is multi-dimension, then getting these integrals is very difficult task. So to bypass this and to get a posterior model probability for model selection, we have utilized the reversible jump Markov-Chain Monte Carlo algorithm. Next. Next slide. So the idea of RJMCMC is we have to pass the posterior distribution and model prior probabilities to RJMCMC. Then RJMCMC defines one universal parameter whose dimension is greater than equal to all the parameter space. Then it does the transition between parameter space and gives us as output a posterior model probability. The model which is having the highest posterior model probability is the best fitted model to the data. Next slide. So we have obtained for our problem the posterior model probability for all the 3 locations, and we found that the model 1 has to be best fitted for the all 3 locations with this posterior model probability. Next slide. So now we get to know about that the nature of our top predator, that means Chitala. That means Chitala is dependent on Mugil and Shrimp for the survival. So using posterior mean as the estimate of model parameter of θ1, we did the future predictions. So dash blue line denotes the future prediction of population size of Chitala. So in all the 3 locations, we observe that there is a decreasing trend in the population size. So to get better insights in terms of probability, we find the extinction probability for all the 3 species in all the locations. Next slide. So for calculating extinction probability, we define Tm, the time to the extinction of Chitala, and probability Tm less than equal to T describes the probability that the Chitala will extinct by time T. Similarly, Tg and Tp are defined. We sample 1000 vectors of parameter value from the joint posterior distribution, which we obtain using JAX program in R. And for each parameter vector, we calculate future trajectory. And during the simulation, if the population size at particular month falls below 1, this we recorded as the extinction event. So out of 1000 event, 1000 times, how many times we get a extinction event? Based on that, we calculate the extinction probability. Next slide. This is the extinction probability. So Chitala is having highest risk in Raidigi and Diamond Harbor, whereas Malancha, Mugil is having the highest risk. But question is, what causes this extinction? So for that, we utilize the Sobol sensitivity analysis. Next slide. Next slide. So Sobol sensitivity analysis gives us the 2 indices, first order indices, which measures the individual input parameter contribution to overall output, whereas the total order indices consider the total contribution of the input parameter, including first order and any interaction of the parameters with other parameters. So these parameters have been calculated by varying parameters in their 95% posterior interval using ODE Sobol function. Using ODE sensitive package in R. Next slide. So these are the average sensitivity plot for the 3 locations. Next slide. Next slide. Next slide. So we found that for Chitala density, 3 parameters are the most sensitive. One is death rate of Chitala, second is the biomass conversion rate from Mugil to Chitala, and third is the predation rate of Chitala from Shrimp. Next slide. So we also calculate the coexistence and stability of species using the parameters from the posterior distribution, and we found that the Chitala and shrimp and Mugil will persist, and Chitala will not persist. Next slide. So these are the results and conclusions of our finding. That means we found the M1 has been best model with the specialist predator. And according to the extinction probability, Chitala is having the highest risk of extinction in the future years. The causes based on the sensitivity analysis suggest that nutrition conversion from the Mugil to Chitala is highly sensitive. So the sufficient nutrition gain to Chitala is not there from the Mugil. Predation rate of Chitala to the shrimp is sensitive. Hence, Chitala may not be efficient for finding shrimp, so they prefer Mugil. So, shrimp and Mugil persist, and the persistent probability of Chitala is very low. So, to conserve this species, we have to look at these three three sensitive parameters. So, thank you.
Thank you, Deepali. That's really great that you made it on time. Congrats. So we have 1.5 minutes if anyone has a quick question. Yes, Katrin.
Hi, thank you so much, Deepali. That was well done in a short time. My question is, you went to a lot of trouble to implement the Bayesian method. And I wonder if you have maybe, could you tell us why you felt that using a Bayesian method was most appropriate thing to do for this problem?
Because for this problem, we have a data of length 60, so which is the short length data. So using the Bayesian analysis, we get the more stable result as per the frequentist approach. So we utilize the Bayesian framework here.
Okay. So did you also try the frequentist method, or?
Yes, I tried the frequentist method with to find the maximum likelihood estimate, and these models are too complex, so the estimate which I am getting are not the stable one. So I prefer the Bayesian framework for this problem.
Okay, thank you.
Great. Thank you, Katrin, for the question. Thanks, Deepali, for presenting. Also, thanks to Sayanti, without whom we wouldn't be able to see the presentation of Deepali.
Yes.
So yeah, that's it. Thanks a lot. Thanks to all presenters, Cynthia, Deepali, and Shireen. The panel of judges, so Julie, David, and Katrin, will discuss, and I will get in touch with you by email as soon as I get their response. Thanks a lot.
Well done, everyone. Thanks. Bye.